Konnichiwa. All right, so let's just jump right into it. So to start off, let's talk a little bit about why we might want computers doing software security. So right now, we have software security assessment, and really it's kind of terrible. So if you think about, you make some reasonable estimates about how many people are writing software and how many people are reviewing software, it's a huge imbalance, which means even if you're writing software kind of slowly, people that have the job of analyzing this software have a lot of work to do. If you just kind of look at the numbers, even if you take kind of an average software analyst with these kind of reasonable numbers, you end up with something like 500,000 lines of code to review a year. And that's really just not feasible. You're never going to be able to do that. And to make things a little bit worse, until you kind of catch up and have people reviewing it at the same speed, you're building up this security debt. So we can think about this kind of as two different problems in networking terms. So you have a bandwidth issue, which is that we have programs being created faster than we have them being analyzed. And we have a latency issue, which is two things. It takes a lot of time to analyze a new program from scratch. And if you ever find a software vulnerability or a bug, it takes a really long time to triage this, figure out the issue, and patch it. So there's a couple solutions. So right now, this is kind of the state of things. We have a high bandwidth input, a lot of software being created. We have this high latency where a human has to analyze things. And then we have a low bandwidth output where this is the actual output they can do. So one solution is, well, I'll just hire someone better, right? I'll replace my software analyst with someone who can maybe analyze software faster. So maybe my latency is a bit better and my output's a bit better. This isn't really realistic. There aren't kind of these magical people that just analyze software twice as fast. So maybe you just say, OK, well, I'll cut down on the amount of software that I produce. Unfortunately, no one's going to do that. They're just going to keep producing more software to stay competitive. So OK, maybe you hire more people. Now, this is great, but it's not really economical. You can't just hire as many software security analysts as you want, that you're going to run out of money. You also have another issue, which is you haven't solved the latency problem. These people will still take a very long time to analyze bugs, and you can't put 3 engineers on a problem and have them work 3 times as fast. So maybe you say, fine, you know what I'm going to do? I'll just replace them all with a computer. This sounds great, and right now that's not exactly what we're going to talk about. This is still quite a while away. But maybe we can do something like this. We have computers and humans working together to try to solve the software security problem. Now, this still sounds kind of far out there. It sounds a lot like science fiction. But this is where we're going to start. So there's luckily kind of a group in the United States which kind of works on these far out science fiction projects called DARPA. So they're the people that have done kind of a few projects you're probably familiar with: GPS, a lot of the technology behind the internet, stealth aircraft, onion routing used in Tor, and so on. And they also host these kind of famous challenges. So the most common example of this that everyone, or a lot of people have heard of, is the DARPA Grand Challenge for self-driving cars. So this was in about 2004, and the idea was, let's try to make cars that can drive themselves through the desert. And here's kind of a picture of one. And if you look at it, this is not something you'd want to drive in, and it's probably nothing you could fit in because there's so many computers there. But now you look 10 years later, and we're actually kind of making progress in this area. So it started out where you had this very rough technology, but today it's a lot closer to reality. And it turns out that the people that have led the Google self-driving car team, for example, actually participated in this challenge. So it's a direct relation between the kind of the work that they had to develop. So the idea was, well, let's do this, but for computer security. Now, this is a lot harder. The computer security problem is not as well defined as driving a car. So we can model it after these capture the flag competitions, which I'll talk about in a second. And of course, to actually get people interested in wanting to work and spend time on this, you have to give them a lot of money. So let's throw some money at the problem and say, if you qualify and you make a good enough solution, we'll give you a bunch of money. And if you actually win, if you can prove that you've created the best system, we'll give you $2 million. And this is what's known as the Cyber Grand Challenge, so what I'm talking about today. And so this is also a good time to talk a little bit about myself. So these CTFs, I've actually been playing them for a really long time with a team called PPP, which is usually the top-ranked team in the world. Sometimes we slip a little bit. I've also graduated from Carnegie Mellon University. That's the team that made that kind of gross-looking self-driving car. But it's a school that has participated in a lot of these challenges and does a lot of this engineering effort. I'm also a researcher at For All Secure. And this is a company no one's ever heard of, that's fine. But we work on kind of automated computer security, which basically means this is exactly what I do. This competition is kind of everything that I've been working on without ever hearing about it. So let's talk a little bit more about CGC. So it's based on an attack defense CTF format. And for those of you who don't know, we'll just go over a brief overview. So the idea is you have a bunch of these different computers, and you have a referee, and you have players. So the idea is the players try to hack into each other. So there are flags associated with services, so things maybe like email servers or web servers. And the idea is if you want to get points, you hack into them over the network, you recover the flag, and then you submit the flag to the referee. And the referee will say, yes, I see that you got the correct flag. So you get some points for capturing it. And green team, you lose a bunch of points because you were insecure. At the same time, you also do something called service checking or availability checking. So the idea here is if you have a web server and you don't want it to get hacked, well, you could just take it offline. And that's not really a valid solution. So what the competition will do is they'll say, OK, is your service running? They'll connect to it and make sure that everything's operating. And if you decide, oh, I'm just going to take my service down, they'll say, is your service running? They'll try to talk to it. And no, it didn't respond. So you lose a bunch of points for that. So just kind of to reiterate, there's a few different things your scores are based on. You have security. Basically, if you lose points if anyone has exploited you. You have offense, which is the opposite. So you gain points if you can exploit someone else. And you have availability, which is that you lose points if you decrease performance or you decrease functionality. So if you break the service you're supposed to be protecting. So DARPA has set this up a little bit differently for their competition. So computers are playing everything, and it turns out that they're running everything too. So rather than having the challengers host their own services, DARPA does it this time. So if you want to patch a program, you give DARPA a patched program and have them run it. If you want to exploit someone, you send a program that sends exploits to DARPA, and they'll run this. So no longer is our architecture like this. It's now kind of like this. So we have a referee which runs its own version of the game. And if you want to talk to it and change services or something like that, you'll communicate through an API. So one of the nice things about this is DARPA now gets a lot more information about what's running on the services. So the availability scoring is very strict when they measure performance, because now they can actually measure the performance of services. If you imagine they tried to do this when you're hosting it yourself, they'd say, did you make the program slower? And you'd say, no, I didn't make the program slower. And of course, they're not going to trust you. But now they're hosting everything themselves, so they can actually measure this. So you lose points for functionality failures, as I mentioned. And the way that this is measured is when people create these challenges in these services, like mail or web or other types of service, you also generate tests. So maybe if it's a mail server, you'll go in and say, yes, I can indeed send an example email, and it works. So you don't see this as a player. You don't actually see this is what it's supposed to do. You're not given a specification that says this is a web server. But you are given the web traffic. So if someone talks to it, you'll see that. And then for availability scoring, as soon as you start kind of decreasing things, if you make it a little bit slower or use a bit more memory, you start losing points. And they have a nice fancy curve that they've developed. And if you look, this is actually really strict. So maybe you think about something like taint tracking, which is kind of a common technology that people use. If you look in academia, taint tracking has about a 15% overhead just for speed. For memory, it's much worse, but just for speed, it's about 15%, which means if you tried to do this, you get about 70% of your score using the state-of-the-art taint tracking, which is kind of unacceptable. You're going to do very poorly if you do this. So you have to come up with a lot of interesting kind of solutions here. So just to go a little bit more detail about how CGC is formatted. So instead of using ELF or Windows files, they create kind of a new executable format that's similar to ELF files. There are only 7 syscalls, which are here. And this is for a couple reasons. So one, it makes running foreign code a lot more safe. So DARPA's running all of your challenges. They don't want you uploading a virus and then kind of infecting their network. But these are the only things you can do. So it's kind of a sandbox in itself. It also makes automated analysis a lot easier. So you don't have to worry about 200 syscalls that Linux has or something like that. From an automated standpoint, you just have to model these few things, which is great. So the first question is, if you're familiar with exploits, you might say, wait, I'm missing things like fork or exec. How do I actually write an exploit in this? So for this competition, they kind of came up with two different things they defined as an exploit. The first type is if you can control a register and the instruction pointer, then that's basically exploitable. It's not exactly the same as a real exploit in kind of modern terms, but if you can get there, then a human could kind of take over and handle everything else. And the second type is if you leak sensitive data. So this is kind of the common thing that you might think of with Heartbleed and something like that. All right, so the first thing to note is that even though you only have these 7 syscalls, there's still a lot of possibilities for complex programs. So you can have several binaries communicating. You don't have sockets, but you do have file descriptors. So you can have maybe 3 binaries that all talk to each other through IPC. You can have user space threading. You can have all this randomness and non-determinism and things like that. And all the code gets compiled down from C or C++ to x86 assembly. So in this format, they kind of created a few different bugs just that people were familiar with, kind of to show that it's not a limiting thing. It's kind of real. So you have things like Heartbleed, as we talked about, the Stuxnet infection vector, crack adder, which is a kind of famous example of a difficult to analyze bug, SQL Slammer, and so on. So the idea is, the bugs themselves aren't important, but you want to show that you're not sacrificing complexity. And if you can analyze these things, you're solving real challenges that are interesting. All right, so let's talk about Mayhem. So this is a system that was created by our team for All Secure. And I'm not going to kind of make this a fancy journey. We were the winning system, yay. So here's a picture, exciting. All right, but I'm going to talk more about the architecture. So the overall architecture was similar to kind of how a lot of teams did it. The idea is, you have a lot of different components, each with different responsibilities, and they'll all talk to each other kind of over one centralized system. So let's go into this a bit more. The first thing you need to worry about is robustness. So we have a completely automated system, and first you need to keep it running. And this is difficult when you don't have people like system administrators. This is kind of a problem that we still have. You're also talking about running untrusted code. You're analyzing binaries that other people are writing, and you don't know what they're going to do. You also have to analyze programs that you've never seen before. I don't know if I'm going to get a mail server, web server, chat server, something completely new. I have no idea, so I can't kind of create heuristics knowing what I'm going to expect. It's also a distributed system. All of these systems are about 2,000 cores across 64 different machines. And now you think, okay, these are all difficult but pretty reasonable problems, but now do this in an adversarial setting, right? Now you're doing this, and you have 6 other teams competing, trying to take your machine offline because they want $2 million. Makes things very difficult and very interesting. So there's a few reasonable things you can do to start. Put things in a sandbox. So for us, ran everything in setcomp, also with resource limits, also inside of virtual machines for hardware isolation. And then we have redundancy. So if one of our machines has a hardware failure, we don't stop the competition and get to start over. So we need to make sure that we can handle any machine failing. And also assume that things are going to fail, things are going to break. So make sure that you can easily detect this with liveness checks, and then make sure that you can start things up again. Now this seems kind of simple, but if you think about it, you look at a lot of antivirus products, for example, and even this first step of sandboxing, they're not doing. So it seems like kind of a silly thing, but a lot of the lessons here really do carry over to other software areas. So, okay, we have a system, it's running. What are we going to do? Well, let's start off by trying to find bugs. So one of the ways we can do this is symbolic execution. This is kind of the standard thing that people talk about in modern academia. So the idea is you'll represent the program symbolically with kind of formal mathematical expressions, and you can use something like a SAT solver or an SMT solver to generate inputs. So just a quick example, I'm not going to go too much into detail, but here's an example kind of pseudo-ish C program. So you take your input, you treat it symbolically. And what you do is you can build up this control flow graph, and you have kind of these gray boxes which are path constraints. So these are expressions that are true or false values. So maybe if this is false, we're going to go here. We're going to return -1. If it's true, we're going to move on to another check, another path constraint. And so we can kind of fill out this whole thing until we've represented this program. And the idea is, if we want to get to that print statement at the bottom, what we do is we take those 3 path constraints in gray, we say, those are all true, and we go to an SMT solver and just ask it for a satisfying input. That's the basic idea. The other way to find bugs that a lot of people work on is fuzzing. This is basically what everyone actually uses today, kind of the industry standard practice. The idea here is you just send values to a program, you execute it, and you see what happens. You can also instrument the program. You might do this because running a program and seeing if it crashes or not doesn't really tell you a lot. Most of the time, it's not going to crash, and you don't learn anything. But if you instrument it, you can do a little bit more. So let's kind of look at our example again from before. We'll cut it down a bit, though. But we can have here, this isn't quite the control flow graph we have, more of a transition graph. So if we throw random value at this, let's say that they're all integers. We throw a random value. With overwhelming probability, it's not going to be 42. And with a tiny probability, it will be. So if we happen to magically guess 42, it's going to go on to this next check. And then if we happen to guess elite, it'll go on to this print statement. So let's think about what happens when we fuzz it. So we throw some random value at the program. Well, of course, nothing happens. It's not that interesting. We picked random values and we weren't lucky. We can kind of guess another random value. Maybe this time we got our B correct, but we're just executing the program. It doesn't know that it's kind of closer, so nothing happens. Again, it goes to the same place. Now maybe we execute this a few billion times, and eventually we get lucky. Maybe we guessed A 42. And so now something interesting happens. The program takes this other branch. And so this is kind of nice because now we've instrumented the program and we see, oh, it took a different branch this time. That's interesting. And so now maybe we keep A as the same value and we only vary B. And so now, okay, that was a bad guess. We can try again. And this time we've gotten it correct. And so the nice thing here is we were able to make these 2 highly improbable transitions one after the other. If we were guessing without instrumentation, the odds of doing this would be something like 2 to the minus 64. However, we have 2 different transitions, which are each 2 to the minus 32, and they don't multiply because we can make this partial progress because we're having instrumentation. So how do you actually do this instrumentation? This is kind of still a problem that we don't really have an answer to. There's a few different tools. QEMU is popular and used in AFL, for example. The issue is all of these slow down your program a lot. So this is kind of a trade-off that you have to make. The whole point of fuzzing is to do things quickly, and when you start trying to work on this too hard, you end up making it slower, and it's not as good as just throwing random values at a program. So let's compare this fuzzing and the symbolic execution techniques. So fuzzing's really easy. You just have to run the program, basically. Symbolic execution, it's a lot of stuff. You have to write all of this additional analysis. Fuzzing, you execute a program very quickly, something like up to thousands of times per second, whereas symbolic execution, you're actually querying an SMT solver, which can be very slow. Fuzzing, you don't really know what's going on, right? You saw this value 42. It didn't know that. It happened to guess it randomly. Whereas symbolic execution, it can understand that. It can say, oh, 42 is an interesting value. I'm just going to try that. Fuzzing is very light on resources, whereas symbolic execution, well, you have to do all this other stuff. You have to represent things symbolically. SMT solvers use lots of memory, et cetera. Now, the benefit of fuzzing is you can take shallow paths and explore them very, very quickly. Whereas symbolic execution, well, if you're patient, it's great because you get to explore nice, deep paths. And in fuzzing, you have to worry about stalling. Maybe you got unlucky and the program, was stuck trying to make one of those highly improbable transitions. And with symbolic execution, you have to worry about path explosion. Programs can be exponentially complex, so trying to represent every possibility might not be feasible. So they both have, their own trade-offs and benefits and disadvantages. So what we did, and what some other teams did as well, is try to do them together. So the idea here is maybe if we just run both of them in parallel, you can kind of get the best of both worlds. So you fuzz a program, and at the same time, you also symbolically execute it. And the idea here is you can kind of do the same thing as you did with fuzzing. You get an interesting input, and you can check if an input is interesting based on instrumentation, and then you can share it between the two. So maybe you get something interesting with symbolic execution, and you feed that back to your fuzzer. Maybe your fuzzer finds something interesting and you feed it back to your symbolic executor. So, okay, maybe we find bugs, but that's not it. We actually have to make an exploit. So there's a couple ways we can do it, but the easy one is symbolic execution. So we already talked about kind of how to navigate somewhere. You have these path constraints and you just feed it to an SMT solver. What if, in addition to the path constraints, you also said, oh, and by the way, EIP is this value, and kind of make that as a pseudo path constraint. Now when you query your SMT solver, it'll get you a solution for this as well. And you can just kind of add these SMT solvers into your exploit code. Now this doesn't always work, so you can also take, again, a hybrid approach where you do both fuzzing and symbolic execution. So you use the fuzzing to try to get maybe more interesting crashes that are maybe closer and easier for symbolic execution to analyze. And then you use symbolic execution to kind of generate an exploit. And it turns out we've actually been able to make some kind of interesting exploits that you might not have expected. So here's some code, and you're probably not going to be able to read it. That's fine. But the basic idea is here's just kind of a snippet. And there's a tiny, very subtle bug in here, right there, or there. So it turns out that this has a null byte overwrite. You're allowed to write a single null byte out of bounds. Now, if you think about this, that's not an easy thing to exploit. So let's talk about how you do that. Well, so in this particular example, it turns out that you can actually overwrite the lowest byte of EBP, the base pointer. And you're doing this inside kind of one layer deep of a call stack. And so it turns out if you overwrite the lowest byte of EBP, of the saved EBP, then the call frame above you is going to use the same base pointer to address a buffer. So if you write to that buffer later, now the address is shifted over and it's going to be incorrect. So if you do this first, and then you send another command to do a separate write, now you're actually going to be able to overwrite EIP. So this sounds pretty difficult, especially if you're not used to kind of exploitation. This is the sort of thing where a talented person could knock this out in maybe a few hours. It turns out in this particular example, our system was able to find the bug and exploit it without any human intervention in 105 minutes, which actually was pretty surprising to us. That's pretty cool, in my opinion. So, okay, now let's talk about patching. The first question is, how are you actually going to modify a program that's given to you? It's compiled, it's stripped, you don't have any information about what it does, so what are you going to do? So there's a few different ways that you can do this. So the first one is binary hot patching. So the idea here is, well, you start off, you just find more space in the program, or maybe you create some more space, and then you redirect control flow there. So we'll go over a quick example. So here's kind of a snippet of assembly, and maybe this comparison line. Maybe you're worried about the value of ECX. So what you're going to do is you're just going to make another block somewhere else in memory, wherever you can fit it. And before you do this comparison, you're going to do a little bit of stuff. You're going to save off some state so you don't clobber anything. You're going to check the value of ECX. Then you're going to restore. And then you're going to do the comparison. So what you can do is now you just overwrite the old instruction with a jump to this new location. So you'll do this kind of instrumented block, and then you'll jump back to where you were before. So the benefits of this is, well, it's really easy to write this. This is kind of the method that most people do when they're trying to do this by hand. And so you're not likely to kind of introduce bugs in the program. But there's a lot of disadvantages. It's really terrible for speed. If you think about something like an instruction cache, every time you're jumping to this distant place, you're totally throwing out all the instructions that you've cached. And it's really terrible for performance. It's also bad for memory performance, because now every time you want to add just maybe a single line of assembly, you might need to create this whole nother basic block in the program, and that's very expensive. So how about this other method? Let's talk about static binary rewriting. So the idea here is you basically just change what you want. And of course that doesn't work, so then you have to go back and fix everything that you broke. So again, let's kind of take the same example. So again, we want to check this comparison instruction. So what we do is we just insert a bunch of assembly. Now you might look at this and say, well, that doesn't quite work. You have a bunch of these addresses, and now the addresses are all totally wrong. So now you have to go back and change all the addresses. And that's basically the entire technique. So this is nice because, well, it's really good for memory performance. You've inserted kind of the minimum code possible. It also has very good speed because no longer are you totally throwing out the instruction cache, you're preserving locality. The disadvantages here, well, every time you miss a single one of those pointers, you totally break the program. So it's a very tricky thing to do. But it turns out this is actually the technique that we favored in our own solution. Now, one last thing that's worth talking about is recompilation. So the idea here is, well, try to take a high-level representation of the program. You don't have this by default, but maybe you can do something like decompile it or lift it to LLVM. And now if you have a high-level view, you can apply high-level patches and then just compile it back down. So here's a basic example. We have some assembly code. We kind of decompile it to this high-level view. Maybe we want to change how the comparison was done. We don't want to check A equal to B. So you apply this high-level patch. Then you can compile that down. And the cool thing here is, your registers may have totally changed around. All the pointers might be totally different. It doesn't really matter because you're a compiler, and compilers can kind of handle all that for you. So the benefits here, well, the performance it's hard to rival this performance. It's basically exactly the same as compilers do, at least in an optimal case. The other nice thing is you can perform high-level patches. So in this case, you can make patches at the source level instead of trying to reason about assembly, which can be kind of annoying. The disadvantage is, well, you need a decompiler. And this turns out to be really, really hard. And the other thing is, maybe you can kind of make an OK decompiler, but now you need a lot of optimizations because, you might lift it to this high-level language, but this high-level language adds a lot of overhead. So when you compile it back down, now your program's 3 times as slow because it's now keeping track of maybe CPU flags that didn't actually matter or something like that. So one cool thing about this, we talked a little bit about instrumentation before. If you have a good solution for patching, you can use this for fuzzing as well. All you have to do is take the exact same thing that you were doing to insert patches, maybe for security checks, and you can use them to instrument your code. So you just insert a little bit of a block, basically the same as you might do if you wanted to insert compile time instrumentation like a tool like AFL might do. So that's kind of a nice little trick. So once you can actually modify a program, what are you going to do? So there's a couple things. So, given a binary, where are you going to apply patches? So the first thing you might think of is, well, I guess every memory access, right? Those are potentially unsafe operations, but programs do a lot of memory accesses. This is going to be entirely too slow. So maybe you say, okay, well, I have like a symbolic executor. Maybe I can prove some of these memory accesses are safe. Well, that's better, but it's still really, really slow. So maybe you develop some heuristics and you say, oh, this memory access looks like it's dealing with a buffer. I know buffers are unsafe. Maybe I'll check this. That's a lot better. It's not perfectly safe. Now you have to come up with these heuristics, and that can be really difficult. So there's a couple other things, and these are the methods that we ended up going with. The first one is wherever you find bugs. Now, this is an obvious choice if you can find all of the bugs, but of course you can't. But it's nice because, you get minimal overhead, right? You're only inserting things where there's actually a problem, and that's great because you're not adding all this extra code. And it also protects all the bugs that you know about, which makes you feel really good about yourself. The other option is maybe you try to patch everything that can affect control flow. So this is a great thing because, you protect jumps, calls, returns, anything like that. And if you've done this properly, you can actually make sure that it's not possible for someone to redirect control flow for your program. Now, this doesn't protect against every single bug. For example, the heartbleed style bugs or logic bugs, this isn't going to break those, but it will protect against someone overwriting EIP if you do the right thing. And there's still a little bit of overhead, but this is significantly easier to do than you might think. Now, the other option is, well, the other thing to think about is, okay, well, I want to patch bugs, but what does it really mean to patch a bug? So, say I've inserted something and I find out that this program crashes, what does it mean to patch something? So, what's responsible for causing the crash? So the first thing you can look at is, well, maybe you have access violations or something. You have an out of bounds write and you saw your crash. So you can look at the registers and say those registers were too big. Or maybe you have an execution violation and so you returned to 0. You had some kind of weird overwrite. So maybe you instrument the program under pin and you go back and you find the return address that did the wrong thing and you say that's the responsible instruction. So if you want to patch it, you just kind of add in a little bit of code that verifies the instruction's not going to crash. Now this sounds great when you first think about it, but you realize this doesn't actually address the problem. You haven't really fixed any bugs. Maybe you've made your program no longer crash, but that's not the same as fixing the actual bugs. And this is a really difficult problem. I don't have a real solution here, but here's an interesting one that we looked into. So the idea is you have a bunch of inputs for your program. So let's throw all of the normal inputs, normal meaning they don't crash. And then you also run the program and you inspect all of the locations around your memory access. So again, let's say it was an out of bounds read or write. You can look at the registers involved in that. And you can actually infer some invariance about the program. So let's imagine that you run through this loop, some random loop in a program. Maybe you run through the loop 100 times and everything's happy, nothing ever crashes. But then you have a bunch of these crash files and you run them and you look and the loop counter is all, 101, 3000, et cetera. What you can do is you can infer that, oh, what they should have done is made sure that this loop never executes more than 100 times. So now when you go to patch it, all you have to do is add back in this invariant that you inferred. Now, this sounds cool, and it works great sometimes, but it's not perfect. It's still complex because you have to infer these invariants, and that's very difficult, but it's at least a start. Now, the other question, well, what if I don't find all of the bugs? Well, that stinks. But you can still apply generic patches. So what I mean by this is basically kind of the standard thing that compilers do to harden binaries. So something like stack canaries. So if you have kind of the call frame for a program, you have the return address, and you stick a canary right before the return address. So now if someone tries to overflow a local buffer, they'll overwrite your canary, and you could say, oh, my canary was modified, this is a big issue, I'm going to abort. You also have data execution prevention. So maybe you look at all of the allocate calls and you try to check for read, write, execute, or something like that, and do something special with them. You also have control flow integrity checks. So maybe you have just kind of the end of a function here and you have a return. So you say, well, what can possibly come after this return? What functions may have called here and where are the valid destinations? And you also have out of bounds read or write protection. So maybe you can say, oh, if you're trying to write to the stack, make sure you're writing not above kind of the local stack variables, or you're not writing outside of my segment. If you normally try to talk to the heap, don't start writing to the stack, things like that. So the issue here is even for compilers, these aren't free. You have a lot of overhead for these. And unlike compilers, we don't even have access to source code, which makes this really difficult. But there's a few things we can do. So we have static analysis, and that's great because we can use that to infer some information. And we can also take a bunch of shortcuts. So let's think about something like CFI. Well, to do this perfectly, you have to know kind of an exact call flow graph for the program. You have to know the entire possibilities for all of the control flow. But you can still kind of do a pretty good job. So even if you don't have this. So let's take the return example we just mentioned. Maybe you don't know all of the functions that could be predecessors to that. But what you do know is that if you're at a return, you came from a call. So you don't necessarily enforce the strictest control flow integrity possible, but you can still say every return must go back to a call instruction or something like that. And this is great because you're only fighting against machines. You're not fighting against humans, so these shortcuts aren't terrible. The other thing you can do is you can get free registers and things like that, the things that kind of a compiler would be able to do as it's running, with doing register coloring and stuff like that. And this helps you generate really efficient patches. And so when you're doing all this, you get to run a bunch of benchmarks and kind of determine, well, am I doing things reasonable? So us, for example, we were actually doing continuous integration tests. So we'd add something like control flow integrity, and we'd say, did this affect things? And maybe we'd say, okay, well, maybe if I do register spilling a little bit different, or maybe saving state a little bit differently, how can this change? And so doing these tests really helped us to kind of figure out what very efficient ways of patching and doing these security checks were. So the problem with performance checking, well, you can only do this when you know inputs. I mean, it's very easy, right? If you know inputs, you just run the valid inputs. You measure the memory, you measure the time, you just calculate the ratio. And if you want to check functionality, you just make sure that whether you patched it or whether you didn't patch it, it always outputs the same thing. And that's great for offline testing when we do our continuous integration test, but what if we're in an actual competition? Here things are really tricky because we don't know if someone's sending junk traffic at us, if this is an exploit, or if this is someone trying to screw around with us, or if it's a real traffic sent from the organizers to try to make sure our service is running. We also don't know if the output from our program is what it's supposed to be, right? If someone exploited us, they could have made our program print something entirely different. So one of the cool things here is we can, again, use our bug finding components. Now, we thought about them as only creating crashes, but things that don't crash are interesting too. because if they didn't crash and we decided to keep them, this means that they used the program in a non-trivial way, right? Because we were doing this instrumentation to say, oh, this explored kind of some new area of our program. And so if we see that this was the case, then it's a very interesting test case. So we can throw it against our program and maybe use this for performance measuring and things like that. Now the next thing to talk about is decision making. So we have this automated system and we need to make very informed choices. So things like, which patch should I apply? Is my system under attack? Which exploit should I be throwing if I have several different ones? And these aren't questions that just apply to this system, right? These are questions that people worry about in their businesses and things like that. So there's a lot of different ways to approach this when you don't have a human in the loop. So one is a fixed strategy. Maybe you say, every time I find a patch, I'm just going to submit it, and that's going to be my patched program. And this is nice. It's very easy to code a fixed strategy. It's never going to surprise you. You know exactly what it's going to do, and you can predict it, and that's nice. It's very comforting. You also have maybe a collection of strategies. So this is nice. So maybe you say, oh, I'm in last place. I should be a little bit more risky about what I do. Or maybe I'm in first place. I should be very conservative. And you can have kind of different strategies that you switch to in different scenarios. This is nice because, again, it's not difficult to code. You can kind of think about specific scenarios and decide what to do in them. And you're still not going to have surprises. And then we have kind of the last thing, which is a fully dynamic or learned strategy. And this is very difficult to code. You're probably going to make mistakes, and it's going to surprise you all the time. But that's not a bad thing. So let's talk about this for a second. This is the method that we ended up doing. And it turns out, pre-written strategies are great if you know everything you're ever going to see. But that's not the case in a competition like this. There's a lot of weird things that you might not expect. Maybe some other team was weaker or stronger than you expected, and that surprised you. Or maybe other teams are finding bugs that you never knew about. Maybe challenges have unexpected bugs. Maybe a bug was written by the creator of a challenge and they didn't even realize it. Or maybe, a team found something that wasn't ever expected. Or maybe things break in kind of new and spectacular ways that you never anticipated. And this is almost certainly actually going to happen. So one of the approaches is Bayesian estimation. And this is what we did. So the idea is you have a lot of information. A lot of these different kind of variables that you can look at, and you can say, some of these you can measure. For example, how likely is it that a team has patched? You can actually look and see, oh, they've patched this program, this program, and this program, but not these other 5. So you say, on average, they patch 60% of their programs. And so now this is interesting, right? Because if they patch something new, that means they probably knew something about it. So you can kind of look at all of these different variables and tie them together in this giant kind of Bayesian expression and come up with something that says, how likely is it that I'm being attacked? So this is really great. The problem here is it's really difficult to tell if you're making a good decision or not. But it turns out that a lot of the decisions that our system ended up making were very intelligent in ways that surprised us. So here's kind of a random screenshot from the competition. So this was some random service. And you look and there are 4 teams that patched it. Our team did not patch it. And you might look at that and say, well, those teams were being smart. I see a team has exploited it. Why didn't you ever patch it? Well, it turned out we were the only team that exploited it. And our system was able to reason and say, well, this was a really difficult challenge. I don't see anyone else that's doing anything that looks like an exploit. So, I'm fairly confident that no one else has exploited this besides me. And so it decided I'm not going to patch it. I'm not going to risk, losing performance overhead or anything like that. And here you can see that was absolutely the right thing. We were the only team that exploited it, and it guessed correctly. Which, again, kind of as the challenge or as the author for this thing, it's actually really surprising to see it making these decisions that I'm not confident I would have been able to make. And it's great. Again, this isn't just applicable for these sorts of games. If you have traffic and you're not sure if it's malicious or benign, maybe you think you're under an attack and you don't know what you should do with your servers. Should you turn them off? What are the benefits of patching the service if someone releases a new patch? Is it going to break things or not? And the amazing thing is, imagine if you could do this all in real time. So, our system could do this in something like a minute. Whereas if you take me playing these competitions as a human, maybe I'll read some network traffic and I'll look at something and say, I don't know what this is. I'll go to someone else and ask them. I'll say, you reverse this program. Does this look bad? And they'll look at it and, oh yeah, that looks like an exploit, we should do something about it. And you take this, and it's this giant pipeline that takes something like 15 minutes, whereas our program can do this very quickly. So kind of tying all this together, what do we do? So we receive a compiled program, then we do two things. We patch it, generate a patched version, and an instrumented version. So we can start using symbolic execution and fuzzing to try to uncover new inputs and interesting things. Most of these are not going to crash, and we can use those to test our patches, both for functionality and for performance. And we can also use all of our crashing inputs to try to generate exploits. And then you win. So where is this going? What's the future of this technology? So the first is testing, right? I mean, imagine you have this in your software development cycle. And some people are working on stuff like this, and I think it's basically going to be a necessity in just a couple years. But you can also do things like test software during deployment. Maybe you never had access to the source code in the first place, and so you couldn't run static analysis software. Maybe you're using kind of third-party products and they won't release their source code. Maybe the vendor went out of business, but you can still test it using these techniques. And this is very close, actually. I mean, this is basically things that we're able to do today with this technology. You can also do a lot of triage and offense research. So right now, if you're doing fuzzing, you probably get a lot of crashes. And most of these crashes are interesting and they should be fixed, but they're not actually security critical problems. And if you have 1,000 of these, you don't really have the time to go through all of them. But the nice thing is if you have an automated system that produces exploits, you know immediately if something's security critical, right? If you can produce an exploit for it, then yes, this is a security issue and needs to be fixed immediately. Now this isn't perfect because there might be things that are exploitable but your system might miss, but it's still a nice kind of first pass. The other area is response. So detecting 0 days, for example. This is something that remains incredibly difficult. And humans take a long time to kind of detect these exploits. So if you could automatically detect exploits and also do things like automatically triage them, and maybe you won't do it all by hand, or you won't do it all automatically, but you might use this to assist humans. And maybe you also use these exploits to create patches like we talked about. That would be amazing. And moreover, imagine if you could do those last three things in a matter of minutes. Now this, is still not quite here, but this is the future that we're looking at. Now the other area is protection. So imagine you could take software that was closed source and apply patches to it. Maybe you're not going to fix every single bug, but you can actually harden it. If you think of something like lazy vendors who still apply software protection mechanisms from the 1990s, if someone is able to find a bug, they're going to exploit it no problem. But if you were able to just harden these binaries and introduce things like randomization or control flow integrity, that's going to do amazing things. You could also test these patches automatically. Maybe you fuzz them and you realize, oh, it actually broke this small functionality. As a large corporation, you're not going to want to run untested patches, but if you could test them automatically, that would be a huge win. So where are we with this today? Well, let's kind of look at maybe our other grand challenge friend with the self-driving cars. So on a scale of this, kind of rinky-dink car that you might have catch on fire in the desert to maybe a Mercedes concept car from the magical future, a Google concept car is about here. They're not fully fledged yet. You're not going to jump in one and drive across the country, but they do a lot of good things, and you're probably not going to die. Well, we're about here. We're several years past this kind of car driving and crashing in the desert. We actually do a decent job. We can run on modern software sometimes, but we're still a long ways off from being able to just solve all of the problems I just mentioned automatically. So what still needs to be done? Well, porting to modern systems. So this is actually partially done. Our system runs on Linux, but it doesn't run on OS X or Windows, for example, and it only runs on x86 right now. Scaling to large-scale programs. We can run things like maybe FFmpeg or ImageMagick. We can't run something like a browser and try to run that whole thing symbolically. It's just too large. Also adding more advanced technologies for exploitation. If you want to know if something's exploitable or not, you don't just want to try a few things. You want to have the full arsenal that humans have, which is very difficult. So what do I think the future is going to look like? Well, I don't think it's this big, scary thing. It's not going to be like the Terminator. It's not like that. I think it's going to be something more positive. It's going to be humans and machines kind of working together to create a lot of new and interesting ideas and new software security solutions. And that's it. Thanks. I think there's time for a couple questions. So, yeah, if people have questions, I can listen to.
それでは、少しお時間ございますので、質疑応答のお時間とさせていただきたいと思います。ご質問ございます方、挙手をお願いいたします。係の者がマイクをお持ちいたします。いかがでしょうか。こちらの方お願いいたします。
Very interesting talk. Regarding the scoring system in the competition, so do I recall correctly that you get points for controlling, for example, a register or, for example, leaking some information? Was that correct?
Yes, that's correct.
Right. So with binary exploits, well, you should be able to detect those and patch those. But what about, let's say, business logic types of issues? Do you see that this same approach could be usable for those as well?
So I think for something like business logic, the idea, well, what would work there is if a business was able to come up with a specification and hand it to you. Without a specification, all we can come up with is say, well, programs should never segfault. That's a true specification, but it's not as tight as it could be. But if someone was able to say, money in an account should never be negative or something like that, or transactions or something should never be negative. If you were able to give us a specification like that, then we could run all these test cases, and again, as we're fuzzing, as we're symbolically executing, we could see if that's ever violated. So I think that's the solution there. The issue right now is software developers hate writing anything additional like specifications, so it's tough, but I think that's where we need to go.
What about finding those specifications automatically in the same way?
I don't know I haven't spent a lot of time thinking about it because it's not been something I've been working on, but I think there's possibilities there. I think there's a lot of work that could be done, and I think a lot of these techniques, like inferring invariance, could apply there if you thought about them a little bit more.
Right. Thanks a bunch.
Sure, thanks. Any other questions?
もう一方いかがでしょうか。こちらの前の方お願いいたします。マイクをお持ちしますのでお待ちください。
Yes. Could you explain me a little bit more about the choosing strategy? I'm very interested in how much human interaction was made in the process, and also your vision in near future.
So the strategy was, probably one of the reasons that our team specifically won. I think a lot of people didn't spend a lot of time on the strategy. So we did a couple things. As I mentioned, we took this kind of very complicated approach where we had kind of this Bayesian thing. And what we ended up doing was we also wrote simulators for the entire competition. So we'd say, okay, this is what I'm going to do. What if another team takes this strategy or this strategy, and kind of play these kind of fake matches and see how we perform. And vision moving forward. So again, the next obvious step is just software testing. This is something that we can do today and find bugs in programs that people actually care about, which is amazing. And I think moving forward, some of the stuff I mentioned, again, I think the next big step will be something like Internet of Things. There's a lot of software that's being created very quickly on very cheap devices, which isn't necessarily security focused. And I think being able to do things like analyze those as quickly as people are putting them out is going to be necessary to kind of make sure that things aren't going.
Okay. So thank you. So you mean in the process by choosing strategy, almost no human interaction was made at your team?
Yeah. So
you mentioned.
So the entire competition was done. No human interaction at all. So we were not allowed to do anything.
So and the next step is the complexity of the environment. You mean the number of the kind and the number of the node, something like that, right?
Yeah. So our system itself was 64 nodes with about 2,500 CPUs and 16 terabytes of RAM. Every single team had the exact same hardware setup so that everything was kind of fair. And yeah, we were basically kind of maxing that out through the entire competition. It was about 20 kilowatts or something of power per machine.
Okay, thank you.
Thank you. Probably time for another question or two, if there are any. If not, also, I mean, I'll be around the kind of conference for the next couple of days, so feel free to always flag me down and say hi and ask me stuff. But if there's no other questions, I guess that's it. Oh, wait. Oh, sorry. Wait.
じゃあ最後に
Sorry.
Thanks for a good talk. I would like to ask, how can you seed your input? You know, when you seed your input to randomize the input, the seed is very important to decide. So this is, I think, because this is also one of my research areas. So I want to see how can you smartly to seed the input to generate and find the proper data fit into the system.
It's a great question. So seeding this is very difficult. I mean, so if you think about something like fuzzing and symbolic execution, it's important to know roughly what your traffic is supposed to look like. So one of the things that we did to start out with is we do get a network tap for this competition. So what we did is we looked at the network data and tried to parse that and turn that into valid seeds. So the way that this worked for us is we'd actually run it against the program. We do things like notice if there was randomness. So we'd run it several times and see if it ever differed. If it differed, we'd try to kind of fix the randomness in kind of weird, complicated ways. If it didn't differ, then we'd say, okay, this is at least a valid network seed. And then we do a lot of min setting. So for those in the audience that don't know, this is basically when you look at the interesting branches that a seed may have taken, kind of take the smallest set of seeds possible that cover all of your interesting cases. So we did a lot of this to make sure, when we shared data back and forth, we only shared kind of the min set. I don't know if that answers.
Yeah, thank you, Dan.
Yeah.
It's a very important question, I think so. Thank you.
Thank you very much. All right, I think that's it. So thank you again.
どうもありがとうございました。